University. He received his PhD in mathematics from UCLA. He was a postdoc at UT Austin. That's where we share some time. And today he's going to tell us about his exciting research on active learning for data-efficient machine learning, graph-based classification, and dynamical systems. So please join me in welcoming Kevin.
Thank you to the organizers for the invitation, and I'm excited today to chat with you all about some of this work that I've done here in active learning. These two specific.
Can you switch the mic on? It's
I guess that's probably important.
Yeah.
Okay, now, hey, look at that technology. I can do this. Wonderful. So yeah, excited to share some of this work that I've done here in these two areas: graph-based classification, applying active learning and graph-based methods, and then also active learning for learning in dynamical systems. And to begin, I want to give a shout out to the collaborators that have been a part of the works that I'm going to talk about today. One of your people here, wonderful Jeff Calder here at the University of Minnesota, but also my PhD advisor, Andrea Bertozzi, Bohan Chen, who was a grad student and now is a postdoc at Caltech, and then environmental scientist John Schwenk at Los Alamos. Those four constitute the stuff I've done with, that I'm going to talk about today with graph-based methods. And then Ufuk and Adam from UT Austin, where Yo-Yo and I were met, the active learning for dynamical systems. So as an outline, first I want to set up where I'm coming from, where I'm thinking about with this active learning paradigm, set out some terms that should be helpful for the rest of my talk, but then dive into graph-based semi-supervised classification and talk about two different acquisition function methods that I developed over there and worked on, and then switch gears, talk about active learning and dynamics, and then conclude. So to begin, active learning. So where I'm coming from, I think the data science or machine learning process can be divided into three main parts, three main phases. Your data collection part, wherein we collect inputs, let's say images with their associated outputs, labels, classifications. And then with that data, we go to this model training phase, wherein we decide what kind of machine learning model we're going to use, whether that's a neural network or other type of model class. And then designing on optimization methods. How are we going to fit that model to the training data that we have? And then the evaluation and deployment, whether that's cross-validation techniques or actual deployment in real-world life situations. I think we generally have these three areas. A claim I'm going to make is that most of the machine learning research focuses on this middle area, the model training. Designing new neural network architectures, coming up with guarantees, generalization guarantees, or about different types of machine learning models, as well as guarantees about optimization methods or designing new optimization methods for more efficient machine learning. But all these sort of depend on an inherent assumption. Oh, it's not showing up. Here, let's see if I go forward more, does it change? No, it doesn't seem to be.
You need to exit the presentation mode.
Maybe. Let's see. Stop share and then reshare. Says I'm sharing, but it's not showing up. Oh, okay, there's that. I go play. Oh. Oh, it seems to be pretty lagged, maybe. Huh. I don't know. because what is shown on my screen is I'm presenting forward on this slide or even to the next slide. So now,
So it's just not showing up on the Zoom or?
okay, now it's showing up. It wasn't showing up on the. It was
Okay.
on this screen. On my screen, it was showing. On
Yeah.
this one, it wasn't showing. Okay,
Sometimes the graph, it's a high resolution graph.
Okay.
Over time, yes.
sounds good. So what a lot of the research here focuses on this step, but sort of with an inherent assumption of this passive, what I'll call passive learning, or this IID assumption that the data that our training data that comes to us in both the forms of the inputs with the associated outputs is seen IID from an underlying data generating distribution. So a lot of the nice theoretical guarantees we have over here sort of really inherently rely on this kind of assumption. What I focus on is this interplay between the data and the training. So in a number of applications, it's easy to obtain the inputs, let's say the images, but not necessarily the labels associated with those images. And so this is where active learning comes in. Can we be judicious? Oop. Should be a little, another thing shown up here. Let's see. There it is. Okay. Active learning, which focuses on actively deciding which unlabeled inputs we want to label that will be useful for our machine learning model. So go into the next slide. Here, yeah. So the paradigm for active learning I'm going to be talking about is pool-based active learning, wherein we have a set of capital N inputs that a point cloud in d-dimensional Euclidean space, where we assume that these points have come IID, where the inputs have come IID from, let's say, a density rel. Say these great points over here, set X. Now there's going to be labels associated with each of these inputs. So Y of these Xi's that belong to some label set. For example, classes 1 through capital K, or in regression setting, maybe those are continuous values. But in our setting here, we're not going to have observed all of the labels for all the inputs. It's only a subset of it. By the term model, I'm referring to the function that maps from these inputs to inferred classifications. That depends on the labeled data. The active learning task then is going to be saying, given that this labeled subset, which currently unlabeled point should I label or query its label for next? Let's say this yellow point here. And then an acquisition function is going to be the term I'm using to say the criterion that helps me prioritize the selection of the next points. So what I'm showing here maybe is on this data set, brighter regions, I'm saying that's where I'm going to prioritize sampling next. And that's caught up in this acquisition function. So then active learning, as I'm thinking about it, is this sequential decision-making paradigm that iterates between selecting input data and updating our model, where there's an additional step of a label query, where we're requesting the label Y of X from a domain expert, a human in the loop, or an oracle, call it. So what do we hope to gain by being active? I'd summarize it in the following way. If we mark as a plot as a function of the number of labeled points we have, if passive learning, this IID setting, achieves accuracy curves that look like this, that as we have more labeled data that has been labeled passively, our accuracy increases. But the hope is that by being active, we can increase that accuracy curve faster, level off at a higher overall accuracy, so that for a desired level of accuracy, let's say this red dotted line here, how many labeled points you'd need in a passive regime is significantly higher than you would need in an active regime. So the benefit you have is you need to label less data in order to achieve this same overall accuracy. So we're trying to, then in active learning, have lower label complexity, while also we want our acquisition function to be inexpensive to compute. We don't want to have to solve a more difficult optimization problem to decide what points to label than we would need to do in just learning our classifier. So these need to be efficient to compute. And then we also need to mitigate sampling bias. The beautiful thing with passive learning is that it's the distribution that we're trying to learn from, right? And by being passive, we are getting access to the statistics of the distribution we really care about. But by being active, we're now biasing the distribution. So we got to be careful about that. So we'll dive on into this first area, graph-based semi-supervised classification. So the setup here, semi-supervised classification, really fits nicely into as a complementary problem to this active learning paradigm that we're talking about. You've got the set of inputs and inputs where a subset is labeled and the unlabeled subset. Now with semi-supervised methods, we use both sources of data to infer a classifier. So where you have unsupervised learning that only learns from unlabeled data and supervised learning that only learns from labeled data, semi-supervised is somewhere in between. It uses both sources. And specifically, graph-based methods leverage this clustering assumption. This is how I like to explain this, that the assumption that two inputs that are close to each other should have similar outputs. And how graph-based methods model this is through the use of a similarity graph, where the graph, the node set, the vertex set of the graph are all the data points that you had. And the edge set is imposed on this node set, where I identify those edge weights by this weight matrix W, where the ijth entry of W represents the similarity, a non-negative weight, the similarity between xi and xj. You can think of a Gaussian kernel or a RBF, radial basis function kernel, or a k-nearest neighbors graph. So where a larger positive value of s of xi, xj means the 2 points are more similar, and 0 if they're dissimilar, or smaller if they're not as similar. With this graph, then we can define, wait. Something's going to pop up. It's going to be great. I'll start talking about it. Hopefully it'll show up. A node function. Our classifier is going to come in the form of a node function that maps from the nodes to k-dimensional, there it is, k-dimensional vectors. So node function u maps from the node set to k-dimensional real-valued vectors, where this k-dimensional vector is going to reflect the inferred classification of the node into one of the capital K classes. That is node function u at a node x, it's k-dimensional vector, and its inferred classification y of x then is going to be the argmax of the entries of that vector. These node functions we can identify with an n by k matrix, real-valued matrix, where the ith row of that matrix is this node function u of xi. And so I'll go in between capital U and lowercase u, but they mean the same node function, but sometimes it's going to be easier to write as capital U, this matrix. So with this, we can define a family of graph-based semi-supervised learning models that have the following form. So the model u hat is going to be the minimizer of the following objective function. So this variational problem has two parts. With your labeled set xl, this term over here is what we call a fidelity term. You can think of it as an empirical risk minimization term, where with a loss function L, this is ensuring that our node function at the labeled nodes is close to the observed labels that we've seen so far. But then this other term over here, this Frobenius inner product, leverages what's called a graph Laplacian matrix L. So graph Laplacian matrix leverages or uses that weight matrix W, and we define a degree matrix, which is a diagonal matrix with the degrees of each of the nodes along the diagonal, where the degree of a node I, di, is the sum of all the edge weights connecting to node xi. So then with the degree matrix and edge weight matrix, we can define different graph Laplacians, combinatorial graph Laplacian, symmetric normalized graph Laplacian, or a random walk graph Laplacian matrix, which are, these objects are heavily studied in spectral graph theory. But for our purposes here, it comes in, is used in this, what we call a graph-Dirichlet energy term. So in the case of a combinatorial graph Laplacian, d minus w here, what that inner product turns out to look like is something that's proportional to the sum over all these edges in the graph, the squared Euclidean distance between the node function vectors, u of xi and u of xj. So minimizing this as a part of this objective function encourages or captures this clustering assumption. Because you can see for for positive weights, wij here, to minimize this, I need u of xi. I'm encouraging u of xi to be close to u of xj. And so where wij's are larger, we are trying to enforce that more, capturing this idea of the clustering assumption. So then active learning problem here with these graph-based semi-supervised classifiers is saying, given a current classifier u hat, again, that depends on the labeled nodes, which currently unlabeled node should I label next? Which one's going to be most useful for my classifier to learn from? And here's just a list of a number of methods and thrusts that I've worked on inside of this graph-based active learning problem. I'm going to highlight 2 of those today. Now, the first one is going to be this model change idea. An idea is that behind this acquisition function is we want to label those nodes that are going to change that underlying model u hat the most. So if our current model u hat, given our currently labeled data, is trying to get a better way of getting these nodes to show up as, I'm assuming these 2 blue nodes are labeled and this red node are labeled with a more bold black. Say those are my labeled nodes. And what I'm showing with the other colors is sort of a spectrum between blue and red, trying to say this is the inferred classification of the unlabeled nodes given our currently labeled. So if that's our current node function u hat, then we can consider a look-ahead model, which says if I were to label another node, which is currently unlabeled, and let's label it with what our current classifier thinks its label should be, then how would the whole model u hat change as a result of adding that 1 point and computing that new node function? Model change, acquisition function, then just computes the distance between these 2. What's the difference between u hat and the corresponding look-ahead model for a given point? So the idea is we want to prioritize labeling those points that are going to change this underlying classifier the most. And more kind of the intuition here is if I'm thinking of like a space of node functions, I'm trying to choose points, nodes that are going to help me take the largest steps here in node function space, helping me to, in a sense, greedily explore node function space from how we label data. So by taking larger steps, hopefully we can converge to the true underlying node function faster. This turns out to be really useful. However, computing this acquisition function is actually difficult and expensive. As you think about it, for each unlabeled node, I need to recompute this u hat. I need to solve that optimization problem, which admittedly is a convex optimization problem if my loss function is convex. But then I've got to solve this for every single unlabeled node. This can be unwieldy. And so we approximate this model change with what we'll call a spectral truncation of your graph Laplacian L. So if you've heard of spectral clustering that leverages this graph Laplacian matrix, what you're doing there is you're taking the eigenfunctions or eigenvectors of a graph Laplacian matrix, and you're embedding your data points according to those eigenvectors. And it's these low-lying eigenvalues, their corresponding eigenvectors, capture a lot of the rich geometric clustering structure of your data sets. And that's kind of the thing behind spectral clustering. So we're leveraging a similar idea here that most of the overall clustering structure of the data set is caught in the information in those eigenvectors. And so we're going to approximate that model change by projecting these node functions onto those eigenvectors, those eigenspaces. What this allows us to do is, once I've computed that partial eigendecomposition up front, this reduces the computational complexity of computing this acquisition function and makes it then more readily usable in different applications. And so,
Kevin,
yes.
So is the graph here always? You don't have to go back.
Oh,
That's
dang it.
yeah. That's, so is the graph here always a complete graph?
No.
No.
A lot of times we're considering k-nearest neighbor graphs.
Okay.
That helps also with the computational complexity, because then as we're, well, I guess once we've projected onto the eigenvectors, then the sparsity isn't what we're caring about. But
Okay.
initially, computing this graph, the edge weights,
Yeah.
doing k-nearest neighbors or approximate nearest neighbor search is one of the things we do to make it more efficient.
So the degree here would be, we would be summing up the value of the similarity function value with
Yes.
whoever is connected to you.
Yeah. So if you're connected to your k-nearest neighbors, that degree is going to be the sum of those edge weights of the k-nearest neighbors. Yeah, exactly. Cool. So then with that approximation, we can come on over to, we've applied this model change acquisition function in a number of applications. One that I want to highlight here is hyperspectral imagery pixel classification, where the idea here is we're taking images no longer just with RGB values, but we're sampling at various wavelengths throughout the electromagnetic spectrum. And so the goal here with these images is we want to classify materials that are present in these hyperspectral cubes. So you see an aerial image, we're taking at each pixel. Now instead of just 3 values, we've got a whole vector of values that are these samples at these different wavelengths. And as I fly that sensor over, in these regions where we've got water or soil or a vegetation, as you line up all of those samples in that pixel, what you get is what we call a spectral signature. And different materials have different enough spectral signatures that actually these graph-based methods are really effective at solving or classifying in these contexts. So soil maybe has a spectral signature that looks something like this. Water is different enough. And then similar soil pixels will have similar spectral signatures. Capturing that clustering assumption is sort of inherent that we try to leverage in graph-based methods. So hyperspectral image pixel classification we've seen a lot of success in using graph-based semi-supervised learning methods. The idea with active learning is coming in to say, okay, I've got this hyperspectral cube, and maybe I've got a bunch of different images. Can I choose a subset of pixels that are going to be a representative set, this labeled set, that I can then use as a seed set when I apply the graph-based semi-supervised learning problem for inferring the classification on new testing set images? And where we've used this was with our collaborator John Schwenk at Los Alamos Labs, who's an environmental scientist, and they're worried about, can we figure out the water levels, monitor the water levels in these remote regions of the Earth, wherein it's going to be expensive to fly scientists out, or it's also going to be expensive to put lots of sensors down and keep them powered. So why not just fly these drones or these satellites over and take these hyperspectral images, and if we can accurately monitor the water levels, identify what's a water pixel, what's a sediment pixel, and what's a land pixel, then we can automate this process more efficiently. And so some qualitative results here with having applied a model change acquisition function for choosing a representative set and applying graph-based semi-supervised learning methods. Here's just 2 different images for some qualitative results. So then the RGB image of these 2 locations look like here on this left column. Right here is the ground truth, meticulously labeled by our colleague, John. Took a long time. I actually don't know how long it took him, but I just am grateful for his efforts on that. Our method, you can see this green is water, yellow is going to be sediment, and blue is land. Qualitatively, you can see there's actually, we capture a lot of the artifacts. Let me stand over here. And down here in the bottom right, there are rivers and parts of the bodies of water that are really difficult to get that we're picking up. That by comparison, is on this far right, this deep water map, which is the de facto standard, this state-of-the-art, deep learning-based classifier for this specific application. It misses a lot of those artifacts. And it adds some other things here in this top image. So this qualitatively looks pretty good, but so for some quantitative results, here's a table of accuracies of a number of different methods we're applying on these sorts of data sets, where there's a little bit to parse here. This top or this right column, OA, is the overall accuracy. The accuracy on a testing set image of pixels that you got classified correctly. But what we really care about are the boundaries. We want to know how the water level is changing, which the middle of a body of water is maybe not as important. It's really these boundaries that are going to be more difficult. And so we also computed what the boundary accuracies, a 3 or 10 pixel neighborhood. What you see is these methods, these C-gap, that's us using this model change acquisition function for identifying a representative set, and then applying graph-based learning, had superior accuracy across the board, both in overall accuracy as well as going to these boundary accuracies. And the main one I want to compare against is this deep water map, DWM-R. So while those boundary accuracies degraded more with the deep water map, using our graph-based methods, leveraging model change for identifying the representative set, we had better performance overall. Besides better performance in terms of accuracy, I want to point out the labeling difference. We only labeled 4,000 pixels using this model change acquisition function, whereas deep water map was trained in a passive manner, needed 2.1 million labeled pixels. So this is one of the successful applications here of graph-based learning, and specifically using active learning to identify good labeled sets. But as I've used model change and thought more and more, I wasn't quite satisfied. It's still pretty expensive to compute. It's a nice idea, model change, for how to prioritize and label points. But this now gets to work that I did with Jeff Calder. And the idea is, could we design something that's cheaper that still allows us to do well and choose good sets? And the idea we go back to is what's called uncertainty sampling. And I'll call this traditional uncertainty sampling. We have our current model U-hat classifier. Doesn't need to be graph-based. Uncertainty sampling is sort of this first idea we try. And the idea is, let's label those points that our current classifier is quote unquote uncertain about. And what's our measure of uncertainty? A simple thing is to take those points that are closest to the decision boundary of our current classifier. Which makes sense. These are in regions where our classifier is not quite sure or convinced that the points are of one class or another. Well, this is nice and cheap to compute because it only depends on our current model U-hat. There's no look-ahead model that we need to consider. While it's cheap, it doesn't ensure what I'll call exploration. And this is reminiscent of the exploration versus exploitation trade-off you have like in reinforcement learning, where in active learning, exploration is trying to label points that explore the clustering structure of our data set to make sure we get good approximate decision boundaries. And then exploitation looks like sampling along those decision boundaries to try to refine them. So this uncertainty sampling, this traditional, first heuristic we always do, it doesn't ensure exploration because it only depends on our current decision boundary. We're not seeing if we've missed another part of the decision boundary. So these are overly exploitative generally, but they're nice and cheap to compute. And so what we set out to do is design an uncertainty sampling method that's tailored to a graph-based semi-supervised learning model that can ensure exploration. And so what we came to is using this Poisson reweighted Laplace learning. And with all apologies to Jeff, I'm going to super oversimplify it. I want to point out he's done a lot of wonderful work in establishing methods like these and establishing a theoretical foundation and motivation for these. So I highly recommend checking out his work. The TLDR here is going to be, I'm going to highlight 3 things. We're going to have hard constraints at the labeled nodes. So those labels that we've seen, at the labeled nodes, we're going to fix the node function outputs to be the one-hot encodings of those labels. We're going to reweight the graph Laplacian near the labeled nodes. And what this does is it helps actually account for degeneracies we have in what we call the low label rate case of semi-supervised learning, when you have small amounts of labeled data and lots of unlabeled nodes in your graph. And then this tau I perturbation you add to the graphical Gaussian, I'm going to call this a tau decay term. Because what that turns out to do is it helps it makes the node function entries of those vectors decay as you go away from the labeled nodes. And that's actually going to allow us to use the following acquisition function as an uncertainty sampling criterion for active learning. We're going to choose to label those points that minimize the 2 norm of the node function outputs at unlabeled nodes. And to get some intuition of what this looks like, I think it's useful to take a peek over at the continuum limit of these graph-based methods. And this is theory stuff that Jeff has established beautifully, along with a number of other people. But the idea is if that point cloud that we have, if we assume that it comes from this underlying density rho, then we could consider the limit as n goes to infinity. Instead of just n, a finite number of points, you can consider recovering that probability density rho in this infinite limit. Now, instead of dealing with a finite graph object, you're dealing with that density rho. And then that graph Laplacian matrix, if things are properly scaled, converges to an elliptic PDE operator. Similar things about the eigenfunction or eigenvectors converging to eigenfunctions, and a number of different deep mathematical connections here. But that's the overall idea. I can consider this continuum limit where now, instead of that finite graph, I'm looking at node functions now is an actual function over, let's say, in the 1D case, a function over an interval, say A to B. So then Poisson reweighted Laplace learning is going to look like, in this one-dimensional case, over this interval, minimizing this variational energy subject to some boundary conditions. At the end of the day, this is the picture I want to get to. What we see over here is in a binary classification case. So now your node function outputs are going to have 2 entries. If we consider just one of those entries, and if I say in this one-dimensional problem here, if I've got a label of 0 at x equals -1 and label 1 at x equals 0 and 1, so you have fixed the values to be 0 and then 1 and 1. And when each of these different colored curves represents different values of tau. And for increasing values of tau, you see these functions decay more rapidly as you go away from the labeled nodes. So again, that node function here in the binary case is going to have 2 different entries. So this would just be one of the entries. The other entry, step over here, would have the flip of this. At x equals -1, you'd be pinning at the value 1. Then here at 0 and 1, you would pin it down at 0. What this tau decay allows us to do is it means I'm not just going to focus on sampling on points between -1 and 0. This is where your usual decision boundary would be. So traditional uncertainty sampling, being exploitative, would focus on sampling points here. But you see with greater tau, I'm actually, this 2 norm is going to be minimized over here on the right. So what we're able to do is with this cheap acquisition function, we're actually going to be able to control exploration versus exploitation by controlling the decay of these functions here. And we actually can give guarantee in a more general setting in higher dimensions. Again, sweeping a lot of things under the rug. But the idea being here, if now in this continuum limit, considering that density rho, if I have a clusterability assumption on rho, essentially that there's regions in my domain, the support of rho, that I have higher density, sort of the idea of clusters, and then a background region of low density values, then given that assumption, we can choose tau sufficiently large such that this acquisition function, this minimum norm, is small outside of those labeled clusters, so in these unlabeled clusters, and the acquisition function values are large close to the labeled points, or large inside those labeled clusters, you can think. What does this end up giving us? This gives us that when tau is large, then we get exploration. You're ensured your acquisition function value is small in those unlabeled clusters. And when tau is small, or closer to 0, then you're getting exploitation, recovering your usual uncertainty sampling. So to illustrate this in another visual example here, I'm going to consider a little toy data set, 8 Gaussian blobs. Actually, what time do we go to? This was how late we started.
I think we started 10 minutes past.
5 minutes.
5 minutes
yeah.
past.
Yeah.
So,
Wonderful. So these 8 Gaussian clusters, where classification goes 0, 1, 0, 1, alternating around. We consider an experiment where I start with 2 labeled points, 1 in each class, but not all the clusters having labeled points. Then have the results of an experiment with a few different uncertainty sampling. Traditional uncertainty sampling is going to be this top row. Uncertainty norm, our method with tau fixed in the middle and tau decaying, starting off large and then going to 0. We're going to be here at the bottom. So what do we see? In traditional uncertainty sampling, what happens actually is by the end, you'll see, so the labeled points are these red stars. See that it's focused on a subset of the boundaries between clusters. That's because it hasn't labeled each one of the different clusters. It doesn't have labeled points in every single cluster. So it's only exploiting the decision boundaries it's been able to, by chance, find. Whereas with tau fixed, our acquisition function, we get this nice smattering sampling of points in every single one of the clusters. So prototype of exploration and prototype of exploitation, but like poor performance. And down here with tau decaying, starting off larger, we've gotten the exploration, gotten points in every single cluster, but then the acquisition function is thereafterwards focusing on the boundaries between the different clusters. A little toy visual here to gain some intuition about how this exploration versus exploitation is manifesting itself here. So going to more high-dimensional data sets, wanted to create a test bed or a setting where we could gauge this cluster exploration versus accuracy. And so the idea was to take MNIST and fashion MNIST and interpret the digits in MNIST as clusters inside of a modified classification problem. So where digits 0, 3, 6, and 9 belong to one class, 1, 4, 7 in a different, and 2, 5, and 8 in another class. Then starting with 3 initially labeled points, 1 per class, so only 3 out of the 10 clusters having labeled points, I can gauge not only the accuracy here on the left, so for MNIST on the top, fashion MNIST on the bottom, accuracy as a function of the number of labeled points, but I can also gauge cluster proportion. What proportion of the clusters have I sampled from at these earlier parts of the active learning process? The 2 curves, there's a lot of curves here, apologize, but the ones I want you to pay attention to are the blue and the yellow. Blue circles and the gold triangles, yellow triangles, are our acquisition function compared to these other acquisition functions. What we see is in both of these settings, and with other data sets that I'm not showing here, we got better exploration performance. We sampled from every single one of the clusters earlier than other methods, even other methods that are more expensive to compute, such as model change. And accuracy in this model, using those labeled points, we achieved similar performance, if not better, as you can see here with fashion MNIST. So the takeaway here being that this is an acquisition function that's nice and cheap to compute, but it also can ensure exploration. So with that, I'm going to significantly switch gears to a different application, a different setting. There's going to be this active learning of dynamics. So what's going to change here is now instead of a point cloud, and we're trying to bounce around and label points in this point cloud leveraging graph-based models, we're now trying to learn a dynamical system that takes as input their current state xt and an action ut. So what we're trying to do is learn a mapping f that models these dynamics that we're able to observe. Okay, so f of xt ut plus some noise potentially to get our next state xt plus 1. So now what we're wanting to do is we want to explore f in as a function on this state action space x cross u. So we can try to, one approach is we can try to come up with a model, maybe inspired by physics or prior knowledge of what f should look like. Or we can take a data-driven approach that takes these observed state transitions and learns a model. Model-based approaches maybe ignore this observational data that we could have, that we can learn from seeing these observations, whereas data-driven approaches might ignore that prior knowledge, maybe, or what Adam has called side information things also. So what do I mean by prior knowledge? As I sort of alluded to, maybe it's an imperfect or first order approximation of the true dynamics that we'd have, or other types of knowledge such as symmetries that we know should be present. But if you consider something like this half cheetah model in the Joko environment, like maybe I have an idea of what the physics should be, but my estimate of the length of the body is incorrect. And so that's going to affect the performance of control problems there. So if the true system looks like this and our imperfect model is here, but it's a starting point, right? It's a place that I can build a model around. So our proposed method is to use a model-based prior model and a data-driven approach to correct that model and better learn the dynamics, but doing it in an active fashion, where we want to sample regions of state action space in an active fashion to more quickly go from an imperfect model to the correct model, okay? We're going to do this in an episodic fashion. So now I'm switching notation. Tau is going to refer to episodes. So in episode tau, we want an exploratory policy to help us learn the dynamics F such that it leverages this prior knowledge, a prior model, as well as information and data that's gained from previous episodes. And in the end, yields a consistent estimator. If our estimator is mu tau, so I add episode tau of this estimator mu, I want it to converge to F as tau goes to infinity, just to be consistent. So how are we going to do this? We're going to construct an acquisition function to prioritize and specifically the discrepancy between what our observed data of the dynamics, our observations of the dynamics say, and what our prior knowledge has said. And we want to find those regions where there's that discrepancy and focus on sampling there first. So explore where our prior does not match the data that we're seeing. And what we're going to take is this Gaussian process model. So we're going to use a non-zero mean Gaussian process where the non-zero mean is coming from that prior knowledge or the model from our prior episodes. So this m tau is going to be our prior knowledge. And so that's going to come in and be our non-zero mean over here. Our observations are going to be in this vector y. And then our observations of our mean function, or our prior function, sorry, prior m tau at the xu's that we've observed so far in our episode are going to be in this vector m tau. So then our mean is this mu tau n, and our variance, or GP here, all that depends on a similarity kernel K that acts on state action space. This pairs xu's. So what that looks like, let's say over here in a simple example, our ground truth function looks like this sinusoid in the dotted lines. And maybe our prior model, we have the wrong amplitude and a little bit of the wrong phase. Then shown here in the dashed line. Then with some observed data, red points here, the red line here is going to be this mean mu function, and our bars around here are going to represent that variance, or standard deviation. So we're able to see the idea we're leveraging here with this, there's this discrepancy between where your prior model is and what we've observed over here. And so we want to try and prioritize as we find these regions where our prior model is not aligning with where our observations are, we want to focus on getting that right first. And so we're leveraging this discrepancy, the prior minus prediction, which comes in as that vector right there, y minus m tau. So then our acquisition function is going to look like the following. So in episode tau, we've observed n data points in this episode. Then we're at a state x, tau n. The action that we're going to choose next, or the utility of an action, then is going to come down to the sum of this discrepancy term plus standard deviation, scaled standard deviation, capturing some idea of uncertainty, as well as a side information term. And the side information term for different applications can be like, if I know certain actions are not going to be safe, I can have a term that helps to capture that side information that influences your problem. So in that example, or a similar example to the one before, if I've got this ground truth function, again, dashed line being our prior, then our mean function, current mean is going to be this blue line, then acquisition function. We can see what happens as we go along here with the little video. As we're sampling points, you see how the acquisition function can change. But we are still going to have higher acquisition function values in these regions where you're seeing a difference between the prior model and where your current mean is. So we'll come back here. Still have these bumps, even though, so that you've got this discrepancy between what we've observed and what our prior model was saying. And then as you get to a new episode, right about here, we've updated that mean function to be what our prior function to be what our previous mean was. And we go along in these different episodes. But the hope is you get something like that looks like this. As we go along, this acquisition function value, they converge, going closer and closer to 0. And so does our prediction mu going to the actual function f. But that example is a little maybe misleading, because in actual dynamical systems and with these different things, we cannot select data arbitrarily. I can't jump around to different x state action pairs arbitrarily. It depends on where my current state is at. And so what we're going to do is solve a control problem at each step, wherein we're going to try to move towards these areas that are, in a sense, unexpected, that have this high discrepancy. So we're going to solve the following non-convex optimal control problem, where I'm planning out an action sequence that evolves, where the dynamics evolve according to what my current model says, but I want to maximize these acquisition function values along that trajectory. And so we're solving this as a non-convex optimization problem. Cool to do. We're solving it with an ICM planner, where the idea there is I sample an action sequence, a number of action sequences. I see which ones would perform the best. I update then my distribution over action sequences and repeat this iteratively. Sample more action sequences, see which ones do better, and update that distribution there. So assuming we can solve that kind of path planning, that control problem there, then under a number of assumptions on our GP and the state action space, then sampling these action sequences based on this acquisition function actually gives convergence of those posterior variance values. So even though we're not targeting high variance regions, we actually can get that as we go more and more episodes, we will get that those variance values will converge to 0. And with an additional assumption, a boundedness assumption on the reproducing kernel Hilbert space associated with that kernel, then this actually implies consistency, that posterior mean will converge to the ground truth dynamics f as you have more and more episodes. In the interest of time, I'm going to skip the proof idea there and just finish up with talking about these different tests and experimental data. So applying this idea on a simple pendulum example, where we've got this pendulum and we want to characterize what the dynamics look like everywhere. If maybe the length of our pendulum, we have the wrong idea about the length of that or the mass that's associated with it, then starting with that kind of prior model, let's see how fast we'd be able to excite the system to be able to observe data and correct the model. And what we actually see is that our method has a greater impact on that data-driven part of this non-zero mean GP model in the following sense. What I've plotted here on the left is the maximum variance or standard deviation across all the state action space. And And blue here is going to represent our method. Orange is OpAx. It's this optimistic active exploration of dynamical systems from 2023. But then you could also consider just a greedy variance, like trying to get your system into these regions of high variance. So while being greedy with variance in your path planning does indeed decrease that maximum variance faster, what we see is a different thing over here when we look at that maximum error between that mean model mu and the true dynamics f. Actually, over here with the greedy variance method, it actually did not do a good job learning the dynamics. OpAx was learning the dynamics, but our combined model, the prior, we had the prior information as well as our acquisition function. We're able to have lower maximal error from the beginning and able to decrease just as well, if not better, throughout all the different episodes. And what you're able to see is that because it really is tied to this discrepancy term. By prioritizing where that prior model is different from what we're observing, we're able to, we're seeing that explicitly maximizing that in this path planning has a direct effect on helping to learn the model more efficiently. So then you can ask, well, how well does the model that we've learned in this model-based plus data-driven approach actually perform on downstream tasks? So if so in this half cheetah model, where we took as a prior model too long of a body, and then we learned this in this mu tau n in a data-driven approach using our acquisition function to guide that. Then with a model that's learned, how well does it do in a task of trying to get the cheetah to run to the right? And we plot the performance, the cumulative reward of our method with that model fixed, the model we learned fixed, plotting that versus if we had known the true dynamics. And what we see here is that actually the performance as compared to the Oracle model is not too much worse. So we've reasonably learned a good model in an efficient manner, in a limited number of episodes. We've been able to learn a better model of the true system that performs well comparatively to if you had known the actual true dynamics. So to conclude, my core takeaway is that I'm interested, and I think we all could be more interested in how training data really affects the performance of our machine learning models. And that if we're more judicious about what training data we have or what data we choose to label, it can have a direct effect on our machine learning process being more efficient overall, reducing the label complexity or the time to train, things like that. Now we need to design acquisition functions that capture the desired structure, both of our model class as well as the data. That's what we saw over there with the model change, as well as especially the minimum norm uncertainty sampling. It was tailored to a specific graph-based semi-supervised learning model to capture what we wanted in an acquisition function. But having an eye towards those things, those acquisition functions that are efficient to compute. Some future directions. Something I'm really interested in is leveraging randomized policies for regression as well as classification, where now instead of choosing points that maximize an acquisition function, can we use the acquisition function to define a probability distribution over our domain? And there's intimate connections with randomized numerical linear algebra, where randomness is utilized for not only computational efficiency, but you also are able to get with high probability, good bounds what those solutions are compared to more direct method solvers. Another thing I'm interested in is these more domain-specific active learning methods for control tasks or similar types of problems. I come from math department. I'm interested in guarantees in computational mathematics, but I'm also interested in these types of problems where you're trying to tailor these acquisition functions to application-specific constraints and different setups. So with that, I'll conclude and take any questions.
All right, any questions for our speaker?
Sure, ask questions. Yeah, thanks for the nice talk.
Thanks.
I of course seen some of the earlier stuff in the talk, but I don't think I've seen the last part of it before. So that's nice. Can you say so in the active learning in this last part, what's an example of like if it were to exploit too much or explore too much, what does that look like for learning this system?
Yeah, that's a good question. Here with the simple pendulum.
Yeah.
So specifically with this discrepancy based,
Yeah.
the important thing we're leveraging there is an episodic setting. Because if I were just saying, okay, one episode and I've just got one prior model fixed, I would only be focusing on that region where I have that discrepancy. Whereas, which maybe at the beginning, as the pendulum is down here, I've explored and I've seen, my prior model wasn't quite right here at the bottom. I'm just going to keep exploring at the bottom. I'm never going to get up to the top. And so that's an important part of the episodic fashion here, which, yeah, it's not quite as translatable as that exploration exploitation as I explained it over there in the graph-based setting. But that's how I would say it is like exploiting too much with that discrepancy acquisition function would look like you would just be down here forever, really getting the dynamics well down there, but not understanding up there. A different way I could imagine being overly exploitative is, actually maybe that wouldn't be exploitation. But that's what I would sort of say would be how I'd characterize exploitation, over exploitation here.
In some other works, like in reinforcement learning is one, they randomly choose. Like they make random actions in some sense, right? Which allows you to explore.
Yes, and
there's some like similar analogs here.
Yeah. Here in the dynamical system, or because in the graph-based learning, I've had thoughts.
Well, there, yes.
The randomized. You could even think if I've got an explorative method and an explorative method, applying that bandit sort of epsilon greedy approach, going back and forth. But over here, because I'm able to do the path planning, and my acquisition function is inherently trying to explore, because it's got that variance as well as this discrepancy term, it encourages the exploration with an eye towards trying to correct the model faster.